Hey guys, Miss Humphrey here. Well, as you can see, I already started taking notes on this page here on page 8, but I really wanted it to look blank. But then my kids interrupted me a little bit, so now there's a little bit of writing on here, but we're starting fresh. So I'm going to cover a couple things up right away so that you can have them revealed to you a little bit later. So the first thing I want to talk about are our 4 thermodynamic processes. That's what we're going to focus on today, is our isobaric, isochoric, isothermal, and adiabatic. These 4 processes are used to describe what happens when I change properties of a gas. We're going to focus on gas like a fixed container, whether it be this balloon, or in this other example, I have a Play-Doh toy that I'm going to pretend is like a piston, where I have a gas inside of it, and I move the piston up and down, like I'm manipulating the fluid inside of that piston. So first thing, when we're thinking about all the manipulations we're about to make to the gas that's inside of this fixed container, whether it be in my little balloon or in my piston, is we're going to be thinking about PV equals nRT. And so you can see it written up here already, but I am going to just put this in context again for you because this will be our first time seeing it. So the equation is PV equals nRT. Pressure, volume, number of moles of gas, universal gas constant, and temperature. And what we're going to be comparing is the properties of the gas before and then after a manipulation. It could be changing the volume. It could be putting the material in some type of Bunsen burner, or putting the material in something to cool it down, like an ice bath. No matter what we do, we're going to think about the equation a little bit differently. First, we're going to set the equation equal to each other for like an initial versus final scenario. So P1 V1 over N1 R1 T1 is equal to P2 V2 over N2 R2 T2. And now, if you're really savvy, you might have already said, like, wait, why are you putting 1s and 2s next to the N's and the R's? Well, it's just because I started writing so quickly. And so, yeah, the amount of gas in here, in my piston, will never change no matter what type of manipulation I make. So the N's can cancel out. Second, it's the universal gas law constant, so my R's can definitely cancel out, which ends up with this equation P1 V1 over T is equal to P2 V2 over T. And so this is where we'll get to see some of our comparisons as we're going through. Our various thermodynamic processes. So let's get started with our first one, isobaric. Well, iso is the beginning of this word, which means the same or constant. And our second side of the word for each of these will give us a hint as to what we're keeping constant. So in all the examples we're about to talk about, what we're going to be doing is we're going to be keeping one variable constant while we manipulate the gas in 2 other ways. I'm going to focus first on just what each of the processes are and how we can observe them with a graph. And then in a separate video, I'll go through kind of some conceptual questions or some conceptual understandings of these. So I'm going to try to keep us on track and not get distracted and just talk about the 4 processes very clinically, and then we'll go a little bit deeper in them in the next video. So in the first video, pressure stays constant. That's telling me that I'm going to change the volume. I'm going to change the temperature, one of 2 ways, and yet the pressure is going to stay constant the whole time. The pressure is going to stay constant the whole time. So if I was going to graph it, knowing that I have pressure P on the y-axis and volume V on our x-axis, what this looks like is a straight line across. A straight line just like that. And I'm going to label these 2 dots as like maybe 1 and 2. And we could be going from 1 to 2 and have our volume be increasing while the pressure stays the same. Or I could be going from 2 to 1, having the volume decrease as the pressure stays the same. Now you may say right here, wait a second. You're telling me that you're going to decrease the volume rather on this container, but the pressure is going to stay the same? Yes. And I'm going to explain a little bit more of that and how the process works in the next video. I just want to make sure that we get the big picture of these 4 processes down here. Now, I want to tell us something or remind us something from our previous video together, or from our class together, really, hopefully, is the idea of work. Work is done when you change the volume of a gas. So whether that be I pull out on the piston to make it so that there's more space for the gas, or I push down on the piston so the space is smaller. I have the balloon and I allow it to expand somehow, or I take the balloon and I squeeze it somehow. Those would be scenarios in which work is done. Now, we should have already had this in our last class together, but just in case, if you do need to write this down one more time, it's on page 6 in our notes. And I will leave this up here for just a second and encourage you to maybe pause the video if you need to remind yourself of internal energy, which can be represented as a E or a U, and what these signs could mean for us, our work and what that means for us, and our heat and what that means for us. I was just looking at this table myself, and one thing I did notice is that it says, so work done on the gas, that means the volume is going down. In this one, it says work is done by the gas, that means the volume is going up. That's an important distinction that I want to make sure that you have for yourself, is how to change that volume in both of those scenarios. So visiting back over to this page, when we talk about isobaric situations, that means work is being done. Work is done in order to change the volume, but have the pressure remain the same. The real question is the work being done by the gas or on the gas? And that will be left to our information. We'll need to know if the volume is increasing or decreasing. So work done by the gas means that the volume increased. And boy, this would be that time to have color coding pens, friend. If work is done on the gas, that means that the volume decreases. Let's also remember, third pen color right now is that when work is done on the gas and the volume gets smaller, work done by the gas is going to have a negative work value. Oh, I hope you got multiple color pens going. And then work done on the gas is a positive W, just to make sure that we can make all those distinctions. We'll talk more about how to achieve these isobaric processes in our conceptual checks below. But let's keep going through just the 4 processes. Let's do isochoric. So again, iso means constant or same, and then choric is for volume. So the volume is going to stay the same. And I'm going to do a totally new color pen just to give me some separation visually. So volume stays the same or stays constant. If I was going to draw that on my PV diagram or on my PV graph, what I'm going to be looking at is a line that's going vertically right here. And let's label this as a 1 and this as a 2. Now again, we could go going from 1 to 2, telling me that the pressure is increasing, although the volume never changes. Or we could be going from 2 to 1, telling me that the pressure decreases, although the volume never changes. Here's the thing about an isochoric scenario. No work is done. How is no work done? Because the volume does not change. How do we know that? Because the volume does not change. The volume is constant. All the manipulations that take place in an isochoric scenario are going to be thanks to either heat or ice. So am I putting it under a Bunsen burner and adding heat, or am I putting it in an ice bath and losing heat? In both of those scenarios. Where this is also going to become important, there's a lot, but I know you can handle this, is if no work is done in any kind here, I'm going to revisit my equation I have in green up top. If no work is done in an isochoric situation, the change in energy is equal to the heat, either added or taken away. Because there's no work done. Work equals 0. And we should say change in work equals 0 joules. Isothermal. Oh, I know you're getting good at identifying what these words mean. So in an isothermal scenario, temperature remains constant. I'm going to switch it up, use some green pens now. Our temperature stays constant. And so check this out. I'm going to have a graph that's going to show, yes, a change in pressure, yes, a change in volume, but a constant temperature the whole time. And so we're going to see a curved graph that looks kind of like that. And we can say that this is point 1 and this is point 2. And so what I see is if I travel from point 1 to point 2, the pressure is decreasing while the volume is getting bigger. Or if I go from point 2 to point 1, the volume is getting smaller, but the pressure is increasing. And this is where I really get to have some fun with this equation. PV equals T. Because I can talk about it all as just one location the whole time, where I'm just changing one of the variables, or in this situation, both variables, to maintain the same temperature the whole time. So the whole time I'm changing either the pressure or the volume, but that temperature stays constant. The last type of process I want to take us through is adiabatic. Adiabatic. I don't see the word iso in this definition, in this word, so you know what? Nothing is staying constant. Not the temperature, not the pressure, not the volume. All three are changing. Here's what is unique here. There's no heat flow in this system. So we'll write that down first. No heat flow. So there's no heat flowing in and there's no heat flowing out. So the pressure's changing, the temperature's changing, the volume's changing, but there's no heat going in the system. So that tells me that our change in energy in this situation is equal to just the work. Because we already said that our change in Q, our change in heat equals 0, because we're not putting any heat in and we're not taking any heat out. And so now our change in energy is going to be related to the work done on or by the gas. Now here's the crazy thing. This graph looks incredibly similar to our isothermal graph. To the point that I would almost argue it's difficult to tell the difference between the two without being given some context. And I'll tell you that in the future, whenever we're talking about isothermal or adiabatic processes, you will be given enough information to make some distinctions between the two. Some distinctions you might hear between the two, or some words to listen for, would be something like the temperature remains the same while, or heat flows into the system, or no heat flows into the system, or while temperature changes. And so, yes, I'm going to agree with you. Those graphs look pretty similar, almost impossible to tell the difference. And so that's where we're going to have to rely on our reading skills and our listening skills to look for the conceptual differences because the graphs are so similar. Well, that walks us through our 4 thermodynamic processes. And yeah, looks like that took just about 15 minutes. Woohoo! Have a great afternoon.